So welcome everyone to the first session of Hotbeds. This session is titled Deus Ex Machine Learning, and we have three amazing talks. The first talk is titled What Are Machine Learning Models Hiding? And is going to be presented by Vitaly Shmatikov. So please come over.
All right. So, let me talk a little bit about machine learning. So, I'm sure you've all heard about machine learning. So, how does it typically work? So, you start with a bunch of stuff. Microphone. You want me to speak on this thing? No, it's all right. I'll just stand here. All right. So, back to machine learning. So how does it typically work? So you start with a bunch of stuff like text, images, could be something sensitive like medical records. You run it through some training procedure, and then you build a model that can solve all kinds of amazing tasks like sentiment analysis, determining if a text is positive or negative, recognizing objects for more biomedical applications, predictive medicines, things like this. So as you know, there have been amazing developments in this over the past few years, performing better than humans at all kinds of tasks. Amazing. But when people build these models, what question do you think they typically ask? Any guesses? What do they ask when they train a model? If you're a machine learning researcher and you have some data set and you build a model, there is really only one question you care about. What do you think is that question? Does it work? Exactly. That's the only question that they ask. So, which means, did it learn its task well? That's the only thing you care about. And how do you think they typically measure it? Accuracy? More precisely, what kind of accuracy?
Precision.
Well, sure, but what I meant is test accuracies. They take some data that they didn't use during training, right? And they measure accuracy on that data. Okay, and if that accuracy is good, if the model performs well on data it didn't see during training, this model is good as far as they're concerned. They publish a high-impact NIPS paper and move on. So what I'm going to do in the next few minutes is try to show you that this way of measuring quality of ML models doesn't tell the whole story, that there are other interesting questions we can ask, especially if we look inside of these models, if we look at what these models are actually learning. Because it turns out that especially with these modern, amazing ML techniques based on deep learning and neural networks, these models, this is not your good old logistic regression or what have you. These are pretty powerful and beefy systems, okay? So they have huge computation capacity and they have huge storage capacity. So these neural networks, it's like hundreds of layers, each layer is thousands of units, floating point parameters. They can really encode a lot of information. So if we look inside of the model and try to analyze it a little deeper, the first thing that you're gonna see is that if you try to understand what it actually extracted from the data and what features it learned, it's actually learning way more than it needs for its primary task. And if you try to visualize the features that it's learning, and I'll make it a little more concrete in a moment, you discover that there is stuff that it learned that is clearly relevant for what it's trained to do. But in addition to that, it's extracting all kinds of information from the data that seems to have nothing to do with its primary task. It's unrelated, it's statistically uncorrelated, but it's still, in the process of learning, this information is being extracted and encoded in the network. So you might ask, so what? So whoop-de-doo. So it learned a bunch of things that it didn't need, but it performs well. So it turns out that these days people use machine learning in ways that go a little bit beyond let's just build a model and use it. So that's just a nice example there. So for example, you could be training a model. So this is actually taken from a model that's doing something for some fairly simple task like gender detection, detecting if the face is male or female. So it turns out that if you look at the internal representation of the features that the model has learned, it has features corresponding to identities of specific people in the data set. So in addition to learning a very generic and a harmless task, male or female, it's also learning like what actual individual people look like. And the reason this matters is that it actually, if you somehow get access to the model and look at what's inside the model, you can learn much more information about the training data set than you learn just by interacting with the model. So it definitely allows things like membership inference, so determining if someone in the training data set. It also, just by looking at the features that the model has learned, occasionally allows reconstruction of training inputs. So you can actually extract very fine-grained information about the data, potentially sensitive data, on which the model was trained. So one big trend these days where this is going to matter is federated learning, also known as collaborative learning. So this is like a big, big idea that's kind of becoming very popular. Google is deploying a system. There are various other systems in the works. And the idea there is that, well, you know, since privacy is an issue, blah, blah, we're going to learn collaboratively. So you have a data set, I have a data set, maybe we'll have data sets, and then we're going to run through some complicated protocol and train collaboratively without actually sharing the data. So lots of proposals for doing this. So it turns out that in the process of doing this collaborative learning, you effectively kind of open the kimono, so to speak, of machine learning a little bit, and you actually expose not just the final model that you produce, but you also expose various, like kind of as the learning is progressing, you're exposing how the model changes. So in technical terms, you're exposing gradients that reflect change in the model. And it turns out that gradients reveal very fine-grained information about the data you're training on. And this is where this point that I'm making, that these models are discovering way more about their training data than they need for their primary task. This is where it becomes very salient, because by doing this collaborative training, you're effectively exposing this extra information, these unneeded features that are irrelevant, but you're nevertheless extracting from the data. Now you're exposing them to the entire world, enabling people to infer all kinds of information about your training data set and learn all kinds of secrets. And this is actually taken from an actual training procedure, and it's kind of interesting. So this represents features learned at different layers of the neural network. So on the right-hand side, I have here the last layer of the neural network, and the features learned here are relevant to the ML task. Unfortunately, you can't quite see this. I'm sorry about how small this is. But there are circles and triangles there, and the purpose of the model is to separate circles and triangles, which doesn't matter what they correspond to. And in the last layer, it actually has learned to separate circles and triangles pretty well. But this is these are lower layers of the model, and you can see that in addition to learning to separate circles and triangles, it also learned to separate blue and red dots. Okay? This is something that the model was never asked to do. This is just in the process of training, it sort of accidentally learned this other feature of the data, that there are blue and green dots inside of it. So why is this relevant? Well, it turns out that as you go through this, then for tasks like sentiment analysis, object recognition, and so on, fairly generic and nice ML tasks, if you can see what the model is actually learning, that is, if you get to observe the features internally learned by the model, so this is what the model is supposed to do, to determine, is the text positive? What is the gender of the person in the image? But if you see this internal information, all of a sudden you can infer much finer grained information. So in addition to learning if the text is positive or negative, you can also figure out who wrote the text, because there are enough features revealed in the internal representation that the model is coming up with to be able to do actually fairly accurate authorship attribution using standard kind of textbook techniques, courtesy of like Rachel and company, to figure out who wrote the text. If the generic task is determining, let's say, the gender of the person or the race of the person and so on, by looking at the features internally learned by the model, you can also figure out things like identities of people in training images. is someone you know in the training data set. You can even, people who are formerly married can find out if their ex-wife is appearing in the images along with some other person. So you can do all kinds of inference like that, even though it has nothing to do with what the model is learning, simply because that information is actually encoded inside the model unintentionally. So all the time these models are learning, they're discovering things about the training data that nobody has asked it to discover. Yeah?
I mean, but people have asked them to discover them. I mean, anytime you're doing unsupervised pre-training or auto...
This is supervised. This is supervised. This is not unsupervised. Like, I'm giving it a task, okay?
But
with labeled data.
But when you're training, like most of the time when you're training these deep learning models, before you get to the supervised part, right? Like you have the unsupervised pre-training part where you train.
Not in this case. Not in this case. Not in this case. This is a purely supervised labeled data. Okay. So these are, let's say, female faces. These are male faces labeled. Please find a please learn to label gender correctly. In the process of doing this, in the lower layers of the model, completely unasked, it comes up with the representations for individual identities. It comes up with features. Is the person wearing glasses or not? All kinds of things. Yes. Well, for starters, we can show that the features that are being learned here are statistically uncorrelated with the thing that I'm asking it to learn.
And is there any way in which you can kind of say prevent the model from...
I'll come to that question in like 3 minutes, okay? Yes, that is a good question. But so let me make one more point and then I'll open it for questions. So once you realize that what you're dealing with here is actually like a massive storage and computing system with huge unused capacity inside. So here it results in unintended learning, but you start getting like all kinds of ideas about what you can do with it. Because in collaborative learning, maybe you can start putting some functionality into it. Because remember, the way this collaborative learning works is you effectively crowdsource the model from a bunch of people. In Google's case, they crowdsource, for example, NLP models from like millions of phones, things like this. But once you have this capacity in there, you realize, well, maybe I can start adding some additional functionality in there. Maybe I can actually modify the model or influence the model in a way that on certain inputs it behaves the way you want it to behave. So for example, this is kind of an face recognition model that has learned to recognize me, but you can modify it successfully to have some additional functionality to make sure that normally it recognizes people correctly, but when I wear my magic glasses, as I'm doing now, it actually has a backdoor. It recognizes me as someone entirely different, okay? And to be clear, some of you might be thinking, oh, that's just like adversarial examples. For those of you who know adversarial examples. This is not an adversarial example. This is deliberately modifying behavior of the model in a way that I want as an adversary. On certain inputs, it's going to behave in the way I choose. It's going to predict certain words in an NLP model. It's going to classify images a certain way. And the beautiful thing about it is that this has no influence on the things that people actually measure when they measure quality of these models. Like, this has no influence on test accuracy. Yeah?
And you didn't poison in on this second set of features you care about.
Right. So effectively, that's sort of. That's a good intuition. Okay? That's good. Yes. So effectively, you add poisoning on. Sorry, this doesn't have a quick question, but in the first order of approximation, you're correct. Yes. So effectively, you're introducing additional features in there. That's what you're doing. So, yeah.
So, can you estimate the capacity you're saying these things to store a lot of
yes,
data?
you can estimate the capacity.
Of one?
It's big. Like the
gigabytes,
word I like to use,
terabytes?
bodacious. What?
Gigabytes, terabytes? Of the neural net representation or whatever?
Enough to
model?
encode like in terms of memorization, enough to encode the entire training data set, like literally encode the entire training data set. In terms of unintended functionality, do whatever you want to do. In a one shot, you can poison the model, even if you're training with millions of people to have this behavior. We have a paper on arXiv that I encourage you all to read. It's called How to Backdoor Federated Learning. I like that paper, well, if I say so myself, but I think this is an important thing there. So please read. All right, so let me now like emphasize this point, is that this extra capacity gives you a way to influence the model directly. So you poison the model. So it's not like conventional data poisoning where you mess with the training data set and the model then does something else. So if this is conventional data poisoning actually doesn't work all that well in this distributed setting. So, and this outperforms that, and it effectively has no impact on main task accuracy. So if you measure how well it performs on its primary task, like facial recognition, LP prediction, it's like there is no impact at all. That's how massively over-provisioned these models are. All right, so let me now kind of conclude with a few points, and then I can answer questions. So as I told you in the beginning, the only question these ML people are asking, smart as they are, is did the model learn its task well? And they do it by measuring test accuracy. I'm claiming that there is another question that you need. I mean, this is of course a very important question, and this is a core question, you know, God bless. But there is an additional question that we need to be asking as security and privacy researcher, and that is, what else did the model learn in addition to learning its primary task? And this is a question that I'm very interested in, that over the past few years we try to kind of investigate from different angles, you know, membership inference, property inferences, collaborative setting, various poisoning attacks, stuff like this. And it turns out that the answer to this question, there are a lot of things that the model, a lot of other things that models are learning that are not captured by test accuracy, such as memorizing training data, discovering user-specific features unrelated, uncorrelated with main tasks, incorporating backdoors of various kinds, unintended behaviors. Lots of things are going there under the cover, which you will never ever notice if all you're doing is measuring test accuracy. So not measured by any of this. So the big question in this field, and this goes to the question that was asked, what we need here is some notion of a least privilege model. Okay, so in computer security, you have the principle of least privilege. You don't need, so that you don't get more information that you need for your task. So we need an equivalent of this in machine learning. We need a way of constructing models that only learn as much about their training data set as they need to do well on the task you gave them, without all this extra stuff that's in there, like memorizing the training data set and discovering unintended features. And I feel like in terms of constructing privacy-preserving machine learning models and machine learning models that don't have unintended behavior and that don't have backdoors, like this is like finding ways of doing this. This is the key to solving the entire area and making substantial progress. So that's it. So now we have a few minutes for questions.
Actually, we have a lot of time for questions, so.
Okay, so an obvious approach here would be differentiate private machine learning. Does that take care of all the problems that you talked about?
No, of course not. No. I mean, for any number of reasons, like you need participant-level differential privacy as opposed to record-level differential privacy, which is hard. Differential privacy by itself doesn't prevent backdoors, okay? Except indirectly some of their mechanisms. I mean, some of these problems are going to be solved, but it's not like the entirety of the answer.
So I could see the situation where you can do a least privilege model in like if it's you're trying to learn a discriminant function, but if it's you're trying to build a generative model, does it still make sense?
I don't know. Why don't you find out and tell the world? Yeah, I have some ideas about how to do it, but it's not like, yeah.
So I assume that for this work, the steps that you did is you trained your model and then you looked at like the features that it learned that it shouldn't have learned, and then when you then introduced features to prevent this, right? Like these kind of like backdoors, like another example into your training data that prevents learning these features that it shouldn't learn. How can you do this in general if you first kind of like need to analyze which features the model might learn?
So certainly if you specifically want to prevent certain features from being learned, there is actually work that comes from fairness in ML from that community on censoring representations where you can prevent a model from learning specific features. By itself, it's somewhat unsatisfying because you're still learning things correlated with those features and so on. So the only hope for achieving something like this, if you can demonstrate certain properties of the training samples you're training on, like there is enough diversity there of a certain kind, which is a little hard to capture. Yeah, it's related to a certain kind of generalization. That's about as much as I can say, like in one sentence.
So this means this method will only work if I have some kind of like metric that I can compute on the training data, where I can say, oh, this training data
Okay.
looks like...
Something like that. I mean, I'm not even proposing a method. I am kind of, putting an idea out there.
Hi, thank you. So I'm kind of questioning the fact that some of the questions you have put here weren't being asked before in machine learning. So let me explain. We have always, there has been loads of research analyzing the complexity of the models, and of course there are various measures of complexity. It's not an easy problem, but it is kind of well known that complexity, higher complexity comes with overfitting, and that hence lower accuracy on your holdout set or stuff, right? So it seems to me that if it wasn't kind of the general question, it was already one of the main questions. So I don't know, can you comment on this? And secondly, I mean, that's it. So I believe some of these questions were already asked. I believe the backdooring of machine learning, of course, was never asked. No, that's very good.
Let me mention one more thing. So when you're absolutely right. They looked at complexity of ML models, and they're concerned about overfitting, okay? As long as they can show that the model generalizes, life is good for an ML researcher. All of these things generalize very well. So the fact that the model incorporates unintended features of the data, it can memorize the entire training data set, as it turns out, and still generalize.
Yeah, but
that's the interesting thing, is that it's still good from kind of standard perspective. So it's not overfitted in the sense that like a ML person would use the word overfitting.
Right. Okay.
So I agree that no one at NIPS would look at this, but it seems that you could probably use regularization to kind of, if they learn the gradient, you're screwed, but like to approach this, like various regularization techniques, maybe?
Maybe.
Yeah, the introduction of backdoors. What's the adversary model? Does the adversary need to control the full training, or is it enough to...
The adversary is a participant in collaborative training. So the model is, I got 100,000 phones jointly training a model. I control one phone.
That's enough?
That's enough to replace the model in a single shot. Sorry about like tooting my own horn here. On archive, how to backdoor federated learning. We put it on archive like two weeks ago. Please read and enjoy. Send me comments, hate mail, whatever.
Hello, and thank you for the talk. So I was wondering, okay, so you can protect against learning a specific set of features that the model cannot learn, but you say yourself there could be a lot of other features that might be sensitive and you're just not aware of. So is there any robust way to make sure that you're learning only what you need to learn, what you're claiming to learn without...
So that's the $1 million question here, okay? Like, solve this problem and come up to the stage next year, collect the petaword. I mean, this is exactly the question I'm asking. That would be an example of a least privileged model where you can provably say, this model only learned as much as it needs to solve its task and nothing more, okay? So that is the question to which I don't have the answer, but I feel it's an important one.
Okay, do you think it's a metric problem? So for example, you just said yourself, the ML people have these metric journal, and they measure the difference?
Well, it's both. I mean, it's both. You need a different way of regularizing your models, which is much stronger than what they do now, and you need a way of measuring that what you did is right. Or some kind of provable argument that demonstrates that you don't need to measure because by construction you do it right. Sorry, there are like hands in the back. Yeah.
So I have the microphone. So I wonder what you think about the approach that was proposed by Google in the last couple of years, PATE and PATE-E, and those are the subsequent papers. So the idea there is
yes.
basically use transfer learning.
So it's a major advance, and B, it doesn't quite solve the problem. In part, for example, for federated learning, this PATE, whatever it's called, is only going to work if the data is ID across participants. They're very explicit about this. The whole thing about federated/collaborative learning that they emphasize all the time is the reason you need to do this is because the data are not ID. It's because your chats are not quite like my chats, and that's where we get the benefit from federated learning. So yes, it solves many problems. It doesn't solve all problems, and unfortunately, as of now, it's not yet applicable to the really interesting setting like Google's very own federated learning. It doesn't work for that.
So are we here in the same problem that we have for anonymization? So I have seen you giving the talk before after all the anonymization things, where the real problem is that we don't know what we're inferring. So I'm seeing your problem here as I have the labels of the target problem, and then as so many other label columns, which is the things that you're training inadvertently.
Right.
But we don't know how many labels are going to come afterwards.
Mm-hmm. Okay, so yes, it's similar, and like in that problem, there was no hope. In this problem, there is hope, because when you're training model, you're training them for a specific task. The problem there was always is that I'm going to anonymize the data for some unknown universe of tasks, okay? Like I'm going to anonymize the data and yet keep it useful for some open-ended set of computations. Whereas here, I kind of know what I want to do. So this is a much more restricted set.
I can understand that, but we also could argue that for anonymization you could do that, and some people want to do that, like, I just want to learn this thing. But the problem is that you don't know what you are not letting the adversary learning. So we don't know what is this other second dimension that is going to come that you may be learning.
Okay, well, I mean, if I had a solution, I'd be advertising the solution. But, yeah.
No, I'm asking, like, is it the same kind of conundrum?
I feel this one is easier.
I'm going to quote him next year on this.
So we have time for maybe one or two more questions.
Are there other types of models other than large neural networks that can encode large amounts of information?
Yes. We kind of haven't looked at this because, neural networks are cool. But, I mean, it's definitely, of course, yes. So, in some sense, some of them like leak information by design. Like if you look at like nearest neighbor models, some of them like explicitly incorporate data points into the parameters of the model. Like the leakage there is not even interesting. There are like actual data points like encoded in the model. The interesting thing about neural networks is that everything in them is empirical, right? So it's very hard to analyze theoretically, blah, blah, blah. But in general, of course, it's related to capacity of the model. So the more capacious it is, the easier it is to incorporate all kinds of stuff in it. But
you think there are likely candidates for other models that suffer from these problems the most?
I don't know. I mean, we've been focusing on deep learning for obvious reasons. But probably.
I think if you look at the capacity of any given model, that's a way. I think if you were to look at the capacity of any given model, like which is done somewhat in learnability, right? Like that'll give you some sort of correlation.
Okay, so let's thank the speaker again.
Thanks.
So.